Hello everyone. In this video, I will demonstrate the functions of analyzing semi or totally transverse mode, centralized discharge mode, electrostatic precipitate mode, and complementary mode. Firstly, I will take a tunnel with two lanes and a bidirectional traffic mode to demonstrate semi or totally transverse mode, centralized discharge mode, which is located in Xinjiang province, China. The interface of air demand calculation will show some difference comparing with unidirectional tunnel. For example, in the second tab, you only need to fill in gradient and cross-section value for one tube. In the Configuration tab, you can see a force table to define the traffic composition. This is usually for tunnels which normally operate in unidirectional mode, but occasionally operate in bidirectional mode because another tube is under maintenance. In this case, usually traffic volume and the type of a vehicle would be controlled. Additionally, the air demand calculation tab also shows some difference. Now, let's demonstrate the robust functions to analyze this ventilation mode. Number 1. Semi or total transverse mode. Firstly, you can define the section length that semi or totally transverse ventilation mode covers. It is useful for those tunnels which are partially equipped with transverse ventilation system. Okay, let's try. Then you can choose between semi or totally transverse mode. Generally speaking, for unidirectional tunnel, semi-transverse mode with billowing airflow is recommended, so the piston effect can be made the best use of. While for bidirectional tunnels, totally transverse mode is favorable. Then you can define the geometric size of exhaust and blowing ducts, friction coefficient, the pressure loss in connection ducts. Then you get the results. The mode, okay. For example, so this is an example. You can see this result. The most important one is the total pressure per meters of axial fans. You can also check the pressure distribution curve along the tunnel in the right figure. Then Number 2, centralized discharge mode. Firstly, you should define the location of the discharge shaft and designate whether jet fans are needed to balance the air pressure in the upstream and downstream section of the shaft. In most cases, you should choose yes. Then, you need to fill in some parameters like the pressure difference between tunnel portal and the shaft top, some loss coefficient, as well as jet fan type and its corresponding discount coefficient, the geometric size of the shaft, etc. Then finally, you get the results like exhaust, exofine, total pressure and its power, and the jet fan number in each sections. Let's fill in some example values. This is a jet fan type, and this is the discount coefficient. Yeah, you can see the results. The most important one is the exofine power, and in this case, the power of the exofine in the shaft is 1,300 kilowatts. Okay. Then I take a unidirectional tunnel with two neighboring tubes to demonstrate electrostatic precipitate mode and complementary mode. Electrostatic precipitate mode is also called ESP mode in short. We need to open another example. Yeah, this example has two tubes with unidirectional traffic mode. We can browse the air demand calculation interface and their results. Then we turn to the ESP ventilation calculation interface. This interface is very similar with the interface of longitudinal ventilation. In the first interface of longitudinal ventilation, in the first tab, firstly you can set the number of ESP stations. Then you can import design parameters like smoke, purification loads and their volumes, position or mileage of exhaust, and blowing outlets. Then click calculation button. The whole tube will be divided into several sections by ESP stations, and then you can see the calculation results for each section in the right tube, like the jet fan number, that is needed to balance each ventilation section. The last ventilation mode is complementary ventilation mode. Let's open another case using this novel ventilation mode. As we all know, some tunnels have a single gradient instead of a reverse V-shape profile. Therefore, you can imagine the air in the downhill tube is relatively fresh, while the air in the uphill tunnel is much more polluted. So it is a creative and economic way to build connecting air ducts to link the neighboring two tubes and lead the relatively fresh air from downhill tube to uphill tube. Meanwhile, lead the relatively polluted air from the uphill tube to the downhill tube. With such a configuration, it cut down the cost of building a ventilation shaft. Yes, this interface is for complementary ventilation mode. To analyze this mode, you need to fill in mileage of main tunnel portals. This grade, this one, and this one. You also need to fill in the mileages of the inlet and outlet of complementary connecting ducts. This one, and this one. And as well as complementary air volumes. This grade. Besides that, you need to designate which future year, the operation speed in both tubes, as well as jet fan type. Then you can get the analysis results, including the concentration value, pressure, distribution, and the jet fan number in each section of each tube. You can dynamically adjust the complementary airflow and the position of connecting ducts to get an optimal solution. Like this. These two buttons are used to adjust the location of the connecting tubes, and this two button is to dynamically adjust the volume of complementary exchanger airflow. Okay, these are for today's video. Thank you for your attention. See you next time.